Good morning, class. So today we will be discussing chapter 2, Chemistry Comes Alive. So with anatomy and physiology, as with any other biology course, okay, chemistry plays a very important role within our body, within the cells. Chemistry is occurring and is happening all the time. Okay, so a basic understanding of chemistry is important to fully understand the functions that the cells go through, and the functions that everything has to work together in order to maintain homeostasis. Okay, so a basic understanding of chemistry is important, and that's what we will talk about. Okay, all right, so matter. Okay, so organisms are composed of matter, and I'm sure you heard this a million times. Matter is anything that takes up space and has mass. Okay, matter can be seen, smelled, and or felt. And just remember that when we talk about weight, you're actually talking about mass times gravity. Okay, weight equals mass times gravity. So your weight changes depending on where you are located in space. So your weight on the Earth is going to be different than your weight on the moon. And then your weight on Jupiter is going to be different than your weight on the Earth or on the moon. Essentially, the force of gravity, okay, is going to be dependent on how large the object is. Okay, so for instance, the force on gravity on the Earth is greater because Earth is bigger than the moon, is greater on Earth than it is in the moon. So you will weigh more on Earth than you will on the moon because the force of gravity is greater on Earth. Okay, your mass doesn't change no matter where you're located, whether it's the Earth, Jupiter, the moon. Your mass doesn't change. Okay, your mass stays the same, but what changes is the force of gravity. Okay, so weight is mass times gravity, so your weight changes because the force of gravity changes. So on the moon, you will weigh less. All right, and on Jupiter, which is way bigger than the Earth, way bigger than the moon, you would weigh more because the force of gravity is greater on Jupiter. Okay, isn't that? But your mass is still the same. So remember, weight is mass times gravity. Matter is made up of elements. Okay, so an element is a substance that cannot be broken down to other substances by chemical reactions. Okay, so a compound is essentially a substance consisting of two or more elements in a fixed ratio. Okay, all right, so we're going to talk about it in the next slide. An element is composed of atoms, okay, of only one type of atoms that gives the element its characteristic properties. All right. On this slide, you see the image of sodium plus chlorine, which go through a chemical reaction to form the compound sodium chloride. Okay, so the elements sodium plus chlorine, so these are two elements that come together through a chemical reaction and they form a compound sodium chloride, which is just table salt. Okay, so this is an example of how a compound is made. All right, so your states of matter. So matter can exist in three possible states. A solid, which has a definite shape and volume. Liquid, which can change shape but has definite volume. So the liquid can change shape depending on what container it is in, okay, but has a definite volume. And then a gas, which can change shape and volume, okay? All right, so now let's talk about how these elements are essential for life, okay? So there are 92 elements, and roughly around 25% of them are essential for life. So you hear the word organic a lot, especially when you talk about food and going to the grocery store. So the way that actually they use organic at a grocery store is actually different from how they use organic in chemistry. The way they use organic at a grocery store, they pretty much are saying that the food hasn't been treated with pesticides or growth hormones, things of that nature. That's pretty much what they're saying. It's all natural. It hasn't been treated with any kind of pesticides or growth hormones. Whereas organic in chemistry means that it's something contains carbon. That's what organic means. They have organic chemistry, which is essentially the chemistry involved of all the different bonds that carbon can form with other elements. Okay, so that's organic chemistry, but it's all centered around carbon. All right, so essentially, from a chemical point of view, okay, anything that contains carbon, all right, is organic. Okay. All right. And carbon, again, with life is a very essential element. Pretty much everything living, okay, everything living contains carbon. All right. And you also have hydrogen, oxygen, and nitrogen, okay, make up 96% of living matter. All right. And then most of the remaining 4% consist of calcium, phosphorus, potassium, and sulfur. All right. And again, you need these elements for different things, build sugar, build proteins, for building DNA, and so forth. All right, then you also have trace elements, or those required by an organism in minute quantities. And we'll talk about this also, because you also know, and again, a lot of obviously vitamins and minerals consist of elements, but when you're in your body, you have enzymes, okay? And enzymes speed up chemical reactions. So for instance, if I say I want my arm to move, I want to move my arm, okay? That's going to involve a lot of synapses, from my brain, and it's going to involve a lot of chemical reactions going on. That's going to allow me to move my arm quickly, okay? And that's going to involve enzymes in your body. Your body uses enzymes or catalysts that lower the activation energy of chemical reactions, therefore it speeds them up. Okay, so without these enzymes, okay, the chemical reactions will be too slow for essentially me to be able to move my arm or to have life, essentially. Okay, and a lot of the vitamins and minerals that our body needs are coenzymes, meaning they take part in those chemical reactions, okay, so that they can occur at a speed that's fast enough for life to occur. Okay, so that's why a lot of the vitamins and minerals that we need are so important, because a lot of them function as coenzymes. All right, so elements in the body. So you got oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. Then you have all those trace elements, all right, in the bottom box, okay? So this table summarizes some of the functions of common elements in the body, talking about oxygen, carbon, hydrogen, and nitrogen. Okay, so oxygen, a component of both organic, carbon-containing, and inorganic, non-carbon-containing molecules, a gas. You need it for cellular respiration. Okay, cellular respiration, you make the majority of your ATP through aerobic, meaning using oxygen. Oxygen is the final electron acceptor in the electron transport chain, and that when it accepts that final electron, oxygen it gets transformed into water. Okay, so very important for that. You can't live without that because we need ATP. You can't make enough energy without oxygen. Okay, and then carbon, again, component of all organic molecules. From chemistry's point of view, anything that contains carbon is organic. Okay, if it contains carbon, it's organic. And everything that's living contains carbon. Okay, so you find carbon in carbohydrates, lipids, proteins, and nucleic acid. Hydrogen, a component of all organic molecules, influences the pH of the body. And that's also very important too, because we were talking about enzymes, and because they're proteins and they function best at a certain pH. If it's too acidic or too basic, the proteins are going to degrade and be not functional. Okay, so that's also important. And then nitrogen, a component of proteins and nucleic acid. Okay, I'm not gonna read through all of these elements and their functions because you can do that on your own. But it goes through calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. Okay. But definitely go through this table because it gives you valuable information about the functions of these elements. All right, so atoms, okay? So essentially atoms are the smallest unit of matter that retain the properties of an element, okay? So like we said before, we have 92 elements, okay? And each of those elements have a specific atom that corresponds only to that element, okay? So again, each of those 92 elements have a single atom that corresponds only to that element, okay? And that's what makes up the element. It consists of these atoms that are specific to that element, okay? And we're going to talk about this in a second, but essentially the way the periodic table is arranged, okay? It's arranged, so the periodic table is arranged by an order of increasing atomic number. An atomic number is the number of proteins, all right, in the element. And essentially, every element has its own specific number of proteins, okay? We're going to talk about this with isotopes in a second, but you can change the number of neutrons, okay? But if it has the same number of protons, it's still the same element. It's just an isotope. And we'll talk about that, a variation of that element. We'll talk about that in a second. But let's talk about the subatomic particles that make up the atom. So the atom has a nucleus, okay? And inside that nucleus, you have neutrons that have no charge, protons that are positively charged, okay? And the atomic number, again, depends on the number of protons, okay? And then you have surrounding the neutron, you have the electrons, okay? And then, so electrons are negatively charged and protons are positively charged. But again, the protons and neutrons are in the nucleus. And then surrounding the nucleus, you have an orbital cloud of electrons, which are negatively charged. So this slide shows you an image, okay, of an atom, the subatomic particles. So like I said, here is your nucleus, okay? So your nucleus, you have your positively charged protons, and your neutrons are neutral, okay? And then surrounding, okay, the orbital cloud surrounding the nucleus, you have your electrons, your negatively charged electrons, okay? So here's just a figure showing what we got through talking about. Okay, so let's talk about the difference between atomic number and atomic mass. Okay, so as I said before, the atomic number is the number of protons in the nucleus. Okay, and every element has a specific number of protons. If you change the number of protons, it's going to be a different element. Okay, you can't change the number of protons. It's going to be a new element as soon as you change the atomic number. Okay, and we'll talk about this with isotopes. But you can have different numbers of neutrons. Okay, and have the same number of protons, and that's called isotopes. And we'll talk about that more in a second. Okay, so a mass number, okay, is the sum of the protons and neutrons in the nucleus. And understand the reason why you might say, well, why don't you include the electrons in the mass number? It's because the electrons are so small and they weigh so little that it's essentially negligible. How much they weigh. They essentially are so light they don't add to the mass. The electrons are so light, so you don't. When you calculate the mass number, you don't even take the electrons into consideration because they're so light. Okay, so you only add up the protons and the neutrons. Okay, all right. So the mass number. So on your periodic table, you'll see your elements written like this. Okay, so you have the symbol of the element. This is helium, He. Okay, your atomic number is at the bottom. Sometimes they reverse it. Sometimes the atomic number is at the top and the mass number is at the bottom. But it's easy to know which one's the atomic number, which one's the mass number, is because the mass number is going to always be bigger than the atomic number. Okay. So again, like I was saying, the atomic number is always going to be smaller than the mass number, except for hydrogen. Okay, so hydrogen does not have a neutron. So hydrogen just has a proton. So its mass number is 1, and the atomic number for hydrogen is also 1. Okay, if there's a picture of a periodic table, just look at that. Hydrogen just has 1, 1. Okay, for the mass number and atomic number, because it does not have a neutron. Okay, so remember, mass number is the sum of the protons and neutrons. All right, so here we have a helium atom. Okay, we have from 2 different models, planetary model and orbital model. But what you see for helium, so let's just go back to the other slide. Okay, so helium, we said atomic number is 2. So if you have atomic number 2, what does that mean? It means you have 2 protons. Okay, so let's go back to our image. So we remember that our protons were positive and they're red. Okay, so we see 2 protons in the nucleus. Okay, but we also see 2 yellow balls, and these yellow balls are going to be the neutrons. So 2 protons plus 2 neutrons gives us atomic mass of 4. So you see right here, mass number is 4. That's taking into account the 2 protons and 2 neutrons. And remember, the electrons are so small and they weigh so little that you don't take their weight into consideration. They don't add to the atomic mass because they're so light. Okay, so the atomic mass is the protons and the neutrons, which is 4 for helium. Okay, so you will write it, go back to this image, you have atomic number 2, mass number 4. Okay. So let's now talk about isotopes. So I've been mentioning them for a while now. So remember, all atoms of an element have the same number of protons. If you change the number of protons, it's going to be a different element. Okay, so all atoms of an element have to have the same number of protons. However, they may differ in the number of neutrons. Okay, and it's when they differ in these number of neutrons, you have isotopes. Okay, isotopes are 2 atoms of an element that differ in the number of neutrons. Okay, and you have isotopes of carbon, you have isotopes of hydrogen. Okay, so and you have these naturally radioactive isotopes. Okay, which are very useful for biological research. Okay, when it comes to dating fossils, you want to give somebody, you want to trace, an artery. You can give them some type of radioactive solution that allows you to do that, diagnosing medical disorders and so forth. Okay, so these radioactive isotopes, particularly carbon and hydrogen, can be very, very useful in biological research. All right, so this is showing you giving someone, I would imagine, radioactive iodine. The thyroid gland needs iodine to synthesize the thyroid hormone. Okay, so I would imagine what they're doing here is they gave a radioactive solution of iodine, okay, which is going to concentrate in the thyroid gland and allow you to image it, okay. And then you also can use it for medical treatments, food sterilization. All right, so here are isotopes of hydrogen. So remember, we said that hydrogen has one proton and no neutron. So this is normal hydrogen right here. You see it has one proton and it does not have a neutron. So remember, normal hydrogen, atomic mass and atomic number are the same because it has no neutron. So this is normal hydrogen right here with one proton. Okay, so this is deuterium right here, which you see it has one proton. Again, it has to have the same number of protons. You change the number of protons, it's a totally different element. So it still has one proton, but in this case it has one neutron. All right, so this is deuterium, one proton, one neutron. And then you also have another isotope of hydrogen, tritium. Okay, tritium, again, you got to have one proton. You change the number of protons, it's a totally different element. So tritium has one proton and two. This isotope has two neutrons. Okay, but again, deuterium and tritium are two isotopes of hydrogen. Okay, and they have the same number of protons but different number of neutrons. Remember, isotopes have different number of neutrons but the same number of protons of that element. And deuterium and tritium are both radioactive. Okay, these are both radioactive. All right, so let's talk more about solution chemistry now. All right, so most matter exists as mixtures. Okay, two or more components that are physically intermixed. And there are three basic types of mixtures: colloids, suspensions, and solutions. And we're going to talk about the difference between the three in the next few slides. All right, so with solutions, okay, so, and we always talk about water is a very good solvent. So that's all that means is water is very good at dissolving particles. Okay, so in a solution, the solute particles are very tiny. Okay, so you can't see it visibly with your eyes. You don't see anything. The particles are so small that you don't see anything, but they are there and they aren't settled in the bottom. All right, they're just kind of all in the mixture, in the water in this case, with tiny particles scattered throughout. Okay, but again, the particles are so tiny that you can't visibly see it with your eyes. Okay, so with the colloid, all right, the particles are getting larger. Okay, so the particles are larger in the colloid solution. Okay, and then the suspension, okay, the particles are so big that you can see them settle out with your eyes, okay? You see the settled out red blood cells at the bottom of this example right here. Blood, and what they did is they probably spun it in a centrifuge, all right? And the heavier objects settle at the bottom, okay? In that case, it's the red blood cells, okay? But those particles had settled out of the solution, all right? And you can visibly see the particles with your eyes with this suspension. So again, solution, colloids, and suspension. Remember, solution, very tiny particles. You can't see them with your eyes. They do not settle out. Colloid particles are getting bigger, okay, but they don't settle out. All right. Whereas the suspension, the particles are so big that you can see them visibly with your eyes and they settle out. Okay. All right, so you have let's go over the terminology of solutions. Okay, so you can have a homogeneous solution. You can also have a heterogeneous solution. But a homogeneous solution are going to have particles that are evenly distributed throughout. So the solvent, which is usually water, is going to be present in the greatest amount, and the solvent is going to be what the solute is dissolved in. Okay, so the solutes are going to be the particles that get dissolved in the solvent, that get dissolved in the water. Okay. All right, so now let's talk about energy. All right, so energy is essential to life. Okay. So energy is the capacity to cause change, and you need energy to carry out all of life's functions. Okay, but you have different types of different forms of energy, I should say. So you have potential energy, which is, think of it as stored energy, like something being very high up in the sky. Okay, it's gonna have high potential energy. Okay. Whereas we use the term kinetic energy, okay, is the energy of motion, okay? It's when something's moving, it's going to have high kinetic energy when it's moving, okay? Now, in terms of electrons, okay, so atoms can get excited. So, like atoms can absorb energy. A lot of times, it's a ray of light. You can with high rays of energy, gamma rays or X-rays. You can excite electrons, okay, and then they can shift to higher energy levels. Okay, and then when they release energy, when they give off energy, they shift back down to that lower energy level, essentially. Okay, so remember those, we talked about how the electrons orbit the nucleus, kind of like an electron cloud. Okay, but they have different energy levels. You have different, think of it as different. If you can draw a circle around the nucleus, then draw a circle around that circle, and then a circle around that circle, and each one of those circles represents a higher energy level state. Okay, so essentially, when electrons get excited, they can go from the lower energy state to a higher energy orbital state. Okay, and then a lot of times when they give off energy, okay, they're going to return back to their low energy state, to that lower orbital. Okay. Hi. And then you can also, with the periodic table, you can know the energy level of the element just by knowing what row it's in. Okay. And again, this is in the chemistry class, so I'm not you don't have to worry about that. But just understand that you can understand, you know the energy level just by knowing what row the element is on the periodic table. So energy is the capacity to do work or put matter into motion. All right, so energy does not have mass, nor does it take up space. The greater the work that is done, the more energy it uses up. All right, so you have different forms of energy. You have kinetic energy, potential energy. You also have chemical energy too. When you convert the sugar into ATP through cellular respiration, that's really changing chemical energy. Okay, but let's focus right now on kinetic energy and potential energy. So remember, kinetic energy is the energy in motion. So when something's moving, it's going to have high kinetic energy and low potential energy. Whereas potential energy is stored energy, inactive energy. I thought about how potential energy deals with how relationship that something can be high up in the air, or it can have but not moving, high up in the air but not moving. It can have a great potential energy, okay? But as soon as you drop it and it starts moving, that potential energy gets transformed into kinetic energy as soon as it starts moving, okay? So now let's talk again more about electron distribution and how electrons are arranged around the nucleus. Now, first thing that you need to remember, okay, so this is fundamental part of chemistry. The reason why there are chemical reactions, okay, the only reason why that there are chemical reactions is because elements want to achieve their most stable, well, actually, I'm sorry, I should not just say elements, electrons. The electrons, let me be more specific, the electrons in the elements want to achieve the most stable energy level, okay? So when the electrons in an atom is in its most stable energy conformation, it is no longer going to be chemically reactive, okay? Soon as the electrons achieve its most stable energy level, okay, the most stable energy level, it will no longer want to react in the chemical reactions, okay? So chemical reactions are driven by electrons trying to reach their most stable energy level, okay? So understand that chemical reactions are driven by electrons trying to reach the most stable energy level. Sometimes that means taking an electron from another element. Sometimes that means giving an electron away. Sometimes that means sharing electrons, okay? But there are different ways that elements do this. But the take-home message is the reason why they're doing this is to achieve the most stable energy level, all right? And so we're seeing a figure coming up that shell and orbitals, okay, I'm using those words interchangeably, okay? So the first shell or the first orbital that's circling that's circle around the nucleus can hold 2 electrons. Second shell, 8 electrons. Third shell, 18 electrons, okay? But the important thing that you need to know is when we start talking about valence electrons in the next few slides. I'll bring this up in a second. So you see right here, here's the atom nucleus. Okay, so you see the nucleus, and then you see the first circle around the nucleus. That's the first shell or first orbital, and it has the lowest energy level. Okay, and then that first shell, you can hold 2 electrons. In that second shell, which is higher energy level, you can hold 8 electrons. In that third shell, the most high energy level, you can hold 18. Now, remember, I talked about how atoms can absorb energy, okay? And when they absorb energy, electrons are going to go to a higher orbital, okay? And then when they lose energy, those electrons are going to go back down to the lower orbital, okay? So this image just so you can visualize what I said previously, all right? And this is just showing you, okay, essentially the bigger the atom, the more shells it's going to have. So hydrogen is very small. It only has one shell. These atoms with two shells are bigger than hydrogen. And then atoms with three shells are bigger, even bigger. Okay, so the larger the atom gets, the more shell it has. Essentially, the more electrons it has. Okay, and you can't remember electrons are negatively charged. You can't just pack a whole bunch of negatively charged electrons near each other because they're going to repel each other. So electrons need some space from each other. Okay, so that's why a lot of this arrangement is driven on the fact that electrons have to be spaced out far enough apart because they're going to repel each other if you make them too close together. Okay, so remember that. Now, when it comes to chemical reactions that I was talking about, so if you go back to the slide, when you look at your orbitals, okay, so you see all these inner orbitals, like, so you see in this sodium, you see this inner orbital right here that's right around this first circle, right around the nucleus. Then you see that second circle. Those are the inner orbitals, okay? So those inner orbitals, they can't take part in chemical reactions, okay? Because they are in the inner orbitals, so they don't take part in chemical reactions. It's the this outer shell, okay? This outer shell, which are called valence electrons. These the electrons in the outer shell are the ones that take part in chemical reactions. Okay, so that should make sense. So the electrons in the outer shell, okay, are the ones, and they're called valence electrons. They're the ones that take part in chemical reactions. Okay, the inner electrons, they don't take part in chemical reactions. So when you talk about valence electrons, you're talking about the electrons in the outermost shell, okay? And it's these valence electrons that mostly determine the chemical behavior of an atom. And they determine the chemical behavior of the atom because they're the ones that take part in chemical reactions. And remember, like I said, the reason why you have chemical reactions is because those electrons, those valence electrons, want to achieve their most stable energy level. All right, and they're gonna go through chemical reactions to achieve that. And there's two magic numbers when it comes to their most stable energy level. Okay, and you're gonna look at it when you look at the periodic table because they're called your noble gases. Okay, so all the way on the far right. On the far right of your periodic table, you have this column, which is it's called your noble gases. Okay, so they get the name noble gases because if you're nobility, right, you don't want to hang out with the common people, with the ordinary people. Okay, you want to be isolated. You want to keep to yourself. Okay, because you are already achieved the most coveted, the highest status in society. So you don't want to. There's no point for you to socialize with other people that are lower stages in society. Okay, so the noble gases are the same way. They have these valence electrons, and the noble gases have achieved the most stable energy level. Therefore, since they're already in the most stable energy level, they do not want to chemically react. So your noble gases are what you call inert. Right here, this word inert, chemically inert, meaning they do not react with elements, so they will not take part in chemical reactions. They have a full shell, valence electron shell. So if you look right here, there's two magic numbers, and 2 only applies to helium. Okay, so helium has 2 valence electrons. Hydrogen only has 1. Just a quick story. So when they first came out with those Goodyear blimps that we see at football games and things, back in the day, hydrogen was way cheaper. It's way cheaper than helium. So they used to fill those Goodyear blimps with hydrogen because it was just cheaper. a cheaper gas. But the problem is you see hydrogen has one valence electron while helium has two. So for this shell right here, since you only have one shell, two is a full valence. It's full. When you have two valence electrons in this first shell, it's full. Okay, so essentially hydrogen, because it only has one electron and its valence shell is not full, hydrogen is highly reactive. So those Goodyear blimps would blow up because hydrogen was highly reactive. So they would blow up in the air and it would be very bad. Okay, so now in those Goodyear blimps, they use helium because helium is stable because you have two valence electrons, and in this first shell, it can only fit two valence electrons. So helium has a full set of valence electrons. Its energy level is the most stable form. It's happy, and helium doesn't want to chemically react with any other elements. And the Goodyear blimps no longer exploded. Okay, so helium is a stable gas that doesn't react with other elements. And these other noble gases, they don't have two valence electrons because their outer shell is bigger. They're bigger elements. The outer shell is bigger. So in order to have a full set of valence electrons, they have 8. 1, 2, 3, 4, 5, 6, 7, 8. And all of the other noble gases have 8 valence electrons. And these 8 valence electrons is a full set for that outer shell for these bigger elements. Okay, and all of these noble gases are chemically inert, meaning that they do not chemically react with other elements because they essentially have the most stable energy form already for their electrons because their valence electron shells are full. Therefore, they have no driving force to chemically react with other elements. All right, so again, I talked about hydrogen. One only has one electron, okay? But in this shell, in this lower shell, 2 electron is full. So hydrogen, very chemically reactive. Helium does not chemically react at all because its outer shell is full with 2. Now lithium is a bigger element, so you see the first inner shell that's full, but you look at this outer shell, you only have one element, and with lithium that means you can have 7 more. 8 is the magic number for lithium to be full, but it only has 1 right here. So I can go ahead and tell you, in lithium's case, in hydrogen case too, it's always easier to give away 1 electron. It's easier to give 1 away than it is to take 7. Imagine trying to pull 7 electrons from another element. It's pretty much impossible for lithium to pull 7 electrons from another element. So lithium is going to give that 1 electron away, and by giving that 1 electron away, lithium is actually going to be more stable, giving it away and happier. Okay. Hydrogen, same thing. It's going to want to give that 1 electron away to something that has 7 valence electrons in it, and it only needs 1 more to have 8. Okay, and that's how you form your ionic bonds. Okay, your ionic bonds, one element is taking electrons from another, the other one is giving its electrons away. Those are ionic bonds. So one's going to be positively charged, and one's going to be negatively charged. Okay. All right, so the octet rule. All right, so again, 8 is the desired electrons in their valence shell. Okay, except for helium. Helium has 2 because its valence shell is so small. It's that 1 first level valence shell. So it can only fit 2 electrons. Okay, so helium can only fit 2 electrons in its valence shell, and it's full with 2. But the rest of the noble gases, they can fit 8. Okay, they can fit 8, and they all have 8, the noble gases, and they're happy and full, and they don't chemically react. But all the other atoms atoms want to either achieve the 8 octet rule. They want to choose the 8 4 valence electrons, and they do that different ways. Sometimes it's giving away electrons, sometimes it's receiving electrons, and sometimes it's sharing electrons. Sharing is called covalent bonds. When you give and take away electrons, that is ionic bonds, okay? And we've been talking about orbitals. I've been using the word orbitals. You can also use the word shell, okay? But it's just a three-dimensional space where the electrons are found, okay? And each electron shell consists of specific number of orbitals, okay? All right, so this is just a figure showing you, again, these are two noble gases, helium and neon. Helium, in this case, it has 2 valence electron, but it has only 1 shell. Therefore, that 2 is all it can fit, and it's full and not chemically reactive. And then you have neon. Okay, if you look in this outer shell, it's valence electron. It has 8 valence electrons in this outer shell, and that's full for neon. And it's also chemically inert. It also is not going to take part in chemical reaction. So again, whole point of chemical reaction is so that these electrons can achieve the most stable energy form, okay? And it's going to want to achieve that octet rule, 8 valence electrons in this outer shell, okay? If it's bigger than helium. So we're going to stop here for part 1 of chapter 2, okay? And then the next online lecture for chapter 2, part 2, we'll talk about the formation and function of molecules, okay? Which depends on the chemical bond between the atoms, okay? And again, we're going to talk more about how sometimes when they have an incomplete valence share, they can either transfer electrons or they can share electrons, okay, so their electrons can achieve their most stable energy level, okay? We'll talk about that in the next lecture. All right, and again, that's the driving force. Remember, that's the driving force for chemical reactions.